Hey guys, what's going on? Today we're going to be looking at the mathematical puzzle commonly known as the Towers of Hanoi. It's a mathematical puzzle that often comes up in relation to math and computer science and where the two intersect. And this is what the puzzle typically looks like in the real world. However, I've created a digital version. My digital version is 2D, you probably can tell that, but it doesn't actually matter. It does not affect the way this puzzle works at all. So let's get into this. So there's basically the goal of the puzzle is to move the whole stack to one of the other pegs. Obviously, all three pegs are the same, so it doesn't really matter which one. But the caveat to this is that we cannot pick up the whole stack as a single unit, and we cannot pick up more, or I should say, we can't pick up more than one disk at a time. Sorry, and we cannot put a disk on top of another disk that is smaller than the disk below it. So, for example, if I move this purple one over to the end, I can now not place the blue one on top of the purple one. Instead, I have to move the blue one over to the middle, and then I can put the purple one on top of it. So as you can see, if we want to move any disk other than the smallest one to a different place, we have to clear out the disks on top of it, and in sort of a I don't know, process or algorithm to do this. At this point, I've done it enough times that I can kind of just know how to do it, but as you can see, it's basically where you just kind of use the other bigger disks as sort of a place to store the disks that you can't currently move because they're trapped under a thing, and I just did that wrong. Oops. Yeah, no. What I should have done is that, move the green one over there, move the pink one there, blue there, him back, him there. Ta-da. Nope, he should be over here. I'm not great at this, unfortunately. You'd think after doing it so many times I would have figured it out. There we go. So, there you have it. I did successfully move them from one to the other side to the other. We had a few missteps along the way, but I think you got the gist of it. It's not too hard of a challenge. The algorithm for it is fairly simple, but it's definitely enough to thwart me. The other interesting thing about this challenge, and something that will sometimes get brought up, especially when you're talking about it in terms of like computer science, is the complexity in terms of number of moves. We can actually calculate the number of moves with the equation 2 to the n, where n is the number of disks we have, minus 1. So with 5 disks, if we moved it optimally, obviously you can take more than this. This is the equation for like the lowest limit. With 5, we would have 2 to the 5, or the 5th, I guess, which would in fact be 2, 4, 8, 16, 32. Yeah, 32, 31 moves. So that's with 5. Things get a lot more interesting when we start increasing the number of disks, and as you can see, we've got this handy disk increaser. So let's actually set this to 32. Disclaimer, it goes up to 512. That's the limit that I somewhat arbitrarily set. At that point, as you can probably tell, I actually don't even know if you can see these, but each disk is like a pixel high, so we're not going to do that because you won't be able to see. So let's look at 32 disks. There's actually an auto solve, and we can see away it goes. It is solving it just as if we were doing it, except we're not, because we're not good at this, and we don't have the patience, because in this case it's taking about a second per move, and we've got 32 disks here. And according to the equation I just told you, which you probably don't remember after one time through, but it's 2 to the n minus 1. So in this case, 2 to the 32 minus 1. Where 2 to the 32 is about 4 billion-ish, a bit more, and the minus 1 has basically no impact whatsoever. And because of that, you know, at this rate, it would take us, I don't know, about 4 billion seconds. which is a lot longer than I want to wait. We can actually turn off the animation where it'll then move 1 disk per frame. So now it's going at 60 moves per second. 4 billion divided by 60 is still a very long time. So yeah, we're not going to sit through this all the way to the end. But as we can see, you know, our original one, we only had 5 disks, so we've got about 6 times more disks, but whereas we could sit through me solving the 5-disk one, this is not 6 times longer, this is exponentially longer. So that's an interesting property that this challenge has. I think it's kind of interesting to watch the computer solve it because, yeah, I'm not good at solving it. So yeah, so check this out. This is a website that you can go to. I'll have a link in the description. Google Chrome is what I developed it in, and I haven't really tested it in other browsers, but they should work. Unless you're using Internet Explorer, in which case, yeah, I'm very sorry. Please use a different browser. But yeah, so check this out. It might work on mobile, might not, depends. Definitely view it in landscape mode. And if it does have problems, just find a computer. But yeah, so check it out. Thanks for watching.